Hi, I'm Metta Spencer. Today, let's talk about rock dust, shall we? I want to talk about enhanced rock weathering and biochar and seaweed, all of which make a wonderful combination of a soil amendment that I think we can help save the world with. And if that seems surprising, it surprised me a while back. Until now, I'm beginning to sort of believe in this. So we have a scattered group of people here in Northampton or someplace, Massachusetts. Is David Demary, who is a farmer and soil chemist. In Vermont is Thomas Fanacor, who owns a rock quarry and is a real expert on rock dust and what that will do to make soil more fertile. In Australia, where are you in Australia these days, Brian?
I'm in the hinterlands of the Sunshine Coast of Queensland, Australia.
Okay, he's also underwater, so it's remarkable how well he does down there with all those fish. And he is an expert on seaweed and marine permaculture. He's the founder and executive director of something called the Climate Foundation in Woods Hole, Massachusetts. And we will have various Pugwash members joining us, coming in and out. I only see two now, and I may not introduce the others as they arrive late. But Evner Taran is here in Toronto, and Peter Meinke is someplace near Ottawa, if I'm not mistaken. Is that right, Peter?
That's right. Yes, indeed.
Peter is the former dean when I first went to teach at the University of Toronto's Mississauga campus. He was the dean of sciences. But
a long time ago.
Long time ago. Anyway, it's nice to see all of you. And this is a topic that is especially, I'm hoping that it will reach a number of Pugwash members. The Canadian Pugwash movement will be having its annual general meeting in a few days. And I'm going to be pitching a proposal that I hope they will take on as a collective endeavor, which involves several different measures that are intended to mitigate or reduce the effects of climate change. And one of them is enhanced rock weathering and the use of rock dust as a soil amendment. So that's what we're going to talk about today. And these experts are all people who know something about the subject or some aspect of it, different aspects of it. So they will have a conversation about the whole general idea. But let me tell you what I think I have learned in the last 6 months or so about this topic. And that is that I'm a great believer in the notion that we must do more than stop CO2 emissions or even methane emissions. We must, in fact, remove carbon from the atmosphere that's already been put up there because we're double the amount that we really should be. So in order to go back to the kind of climate that we had, which was livable, we must actually somehow suck carbon out of the atmosphere that has already been put there over the last several hundred years. And there are various ways of doing that to restore the climate as it used to be. And nature has its own way of doing that. And that is that we have rocks that simply absorb carbon. So when it rains, carbon is captured in raindrops, falls on rocks. And these rocks will capture some of the CO2, and eventually it gets washed off into the ocean. It makes fizz water, if you will, like bubbly water, and then it's taken up by clamshells and lobsters and corals and things, and and falls to the bottom of the ocean. So it would be nice if we could speed that up, and indeed we can, because the amount of carbon that is taken up by the rocks depends on the surface of the rocks. And if you pulverize rocks and make them into tiny pieces or even powder, there's more surface area, and therefore they can absorb more of the CO2 and handle it for us and really put it away permanently, because for all practical purposes, once the carbon is absorbed and taken up by the rock, it's there for maybe a million years. It doesn't get out again. So that's as a chemist, I think I got a C in high school. So my question, my ability to explain this is probably a bit lacking, but somebody can make up for it. Now, my other concern is that this measure, which is, I'm going to promote the idea of smashing rocks into powder and dispersing that powder on the soil or in the soil. That has value in itself, because we have to get away from using so much fertilizer. Fertilizer has been the blessing and the curse of it's a very double-edged sword, because it has about half of the food in the world today is produced by using fertilizer. And if we didn't have the fertilizer, we wouldn't have the food. So this is a very important essential ingredient to farming. But at the same time, the excess amount of nitrogen and phosphorus and potassium that gets left in the soil and gets washed off into the ocean and so on, that causes pollution, which causes eutrophication of the lakes and streams and so on. It is a very serious global problem. Yet we're going to have to produce more food, because we know our population is increasing. So we have to produce more food in the future, but doing it with less fertilizer. So what are we going to do to make up the difference? Well, rock dust. That's part of it. But then rock dust, you don't want that to go washing away into the ocean immediately either. So how are we going to hold it in place? Well, there's this stuff called biochar, which is basically just charcoal. But you could put, charcoal in the soil along with the rock dust, and that will retain everything that's nearby. It sucks it up like a sponge and holds it a very long period of time, so that you don't have stuff washing away. And that's the reason you want to put your biochar in with the rock dust. And in addition, there are other ways of capturing CO2 in the ocean in a large scale. By seaweed does so, and it is extraordinary in the amount of CO2 that it can capture. So if we can take out some of that seaweed after it's been captured and use it for good purposes, as well as expecting some of it to fall to the bottom of the ocean and sequester carbon that way. But the amount that we take out could be made into a biostimulant that is actually helpful to producing more and more and better food. So the combination of these three ingredients, rock dust, biochar, and seaweed, I think has a great deal of promise. And I didn't invent it all myself. I have to say other people have mentioned some version of what I'm proposing. And my experts here can all explain how I have just completely garbled the whole story and how I've got it all wrong, but please straighten me out.
Well, you've done a great job. I think you've captured it in a nutshell, the prospect. And I guess the question is how do these materials actually work together in the field? In other words, how do you combine various rock dusts and biochar and seaweed together in a whole systems approach, so that you're not wasting effort, whether it's going over the field more than once or building inefficiencies into the program, so to speak, in order to mitigate climate change. So I think that from my perspective, and I've done some writing on it, quite quite a bit of work in the field proving some of these things, is that in order to mitigate catastrophic climate change within a reasonable period of time, which is what we really need to do, we have to combine various methods, materials and methods into sort of a unified strategy. And so that's really the thrust of my approach, is not just working with a rock dust material or biochar or seaweed together, but try to put these things together into a unified strategy, and also look at the way large scale land use and land management is currently being practiced, to see if there are improvements that can be made. As you mentioned, use of synthetic fertilizers, monoculture in general tends to take up a lot of fertilizers the way it's being practiced right now. So there's a number of things that we could do in a whole systems approach that would integrate these materials and methods into a unified strategy. But I do think that your description was quite good, actually. I mean, they're in a nutshell, I think you presented it quite well.
Thank you, Brian Van Hertzen.
Yes, I think I agree with what Tom's saying, and embracing that and adding to it is that we do need to get these systems to work together in an integrated way. And I'd say one key part of all this is having the rock dust available, which provides the mineral phosphate and other micronutrients that are important for plants to grow. Healthy soil microbial communities are provided by appropriate compost, and that compost is going to be very important. In fact, the char that you mentioned is a high quality charcoal that tends to have a large surface area per gram, if you will, sometimes hundreds of square meters per gram. So it's a really impressive surface area, and also a high cation exchange capacity. And it turns out a lot of those cations are supplied by the rock dust, and that's really substantial. They also provide habitat for those healthy soil microbial communities. And so if you end up developing a compost with biochar and perhaps rock dust, it ends up really developing that integrated blend. And those healthy soil microbial communities have within them mycorrhizal fungi and other fungi that will excrete enzymes and help to unlock the phosphate and other minerals from their mineral form into bioavailable form. And those mycorrhizae actually form a network that actually convey a lot of that bioavailable phosphate to the roots of the plants. The roots of those plants actually convey sugars and which are developed into higher molecular weight organic molecules that form humus. And that effectively regenerates a healthy soil microbial community. And then finally, seaweeds can serve as a prebiotic that actually provide essential soluble fiber and other plant growth regulators that facilitate the growth of those healthy soil microbial communities in the soil, and facilitate and help to upregulate the gene expression of the plants that are growing in those soils. So it is a very integrated picture, but that's our improved, let's say, biological understanding of the soil, and how the chemistry and biochemistry of the rock dust combine with the habitat forming properties and the structure of the char and the soil microbial communities to facilitate improved plant growth with a reduction or even elimination of traditional NPK fertilizers.
Mm-hmm. Now, you're the seaweed man. I can even see some seaweed right behind your ear, which is a good thing to show us. I think it may be kelp or something. Now, but please, I didn't even attempt much to explain what the value of seaweed admixture would be. I presume that we're not talking about putting large quantities of seaweed into the soil or into the mixture. But some which would add certain kinds of nutrients. Can you tell us what the value, if any, is of adding some seaweed either as pulverized and mashed up or something, or as a chemical biostimulant? I suppose you make it into a liquid that can be poured in or something. Explain the seaweed part, please.
Sure thing. All across Canada, I would say, and the more subtropical regions, seaweed can be grown offshore, whether it's off British Columbia, Hudson Bay, or the east coast of Canada, and effectively provide well-established agricultural amendments that have a proven ability to increase the production or the yield per hectare in the range of 15 to 30% for most flowering plants. Now, what's especially interesting in this day and age of high fertilizer costs is that it's possible to actually reduce the amount of nitrate fertilizer that's required on agricultural crops while maintaining yields. And the significance there is that the liquid plant growth biostimulants actually have in them a variety of plant growth regulators, including glyberillins, cytokines, and auxins, all within an organic whole food product. And when applied at as small amounts as 1 liter per hectare, they have almost a catalytic effect on the upregulation of gene expression of the plants. And
Did
you're
you
able
say 1 liter per hectare?
1 liter per hectare per week across,
No
multiple.
kidding. That's phenomenally small. You're kidding.
That's because this organic product has these plant growth regulators, including auxins, cytokines, and gibberellins. And these effectively get sprayed onto the leaves of the plant in the morning. They go into the stomata and they upregulate the gene expression of those plants and improve the uptake efficiency of the macronutrient nitrate and the micronutrients, including the micronutrients from the rock dust, into the plant. And so the plant actually produces the same yield with 20% less fertilizer, 20% less runoff, and 20% less nitrous oxide production in the soils. And that's a huge emission reduction. We're estimating 30,000 tons of either emission reductions that per square kilometer of kelp that you grow and sustainably yield. That results, the agriculture associated with it provides a profound amount of carbon emission reduction, and that comes from 20% less nitrate fertilizer produced, 20% less nitrous oxide emitted, and effectively around 8,000 tons per square kilometer per year of seaweed that falls off the platform during growth and sinks 1,000 meters a day to abyssal seafloor, where it can remain for centuries in deeper waters.
Mm-hmm. Okay, well, that's itself very, very interesting. The notion that what you're doing is taking the carbon out of the atmosphere by the kelp or the other seaweed. Some of it is automatically going to fall, and you're pretty sure it's going to go to the bottom where it's going to stay.
So you actually measure the seaweed.
What fraction of the say if you have a kelp farm, what fraction of the kelp is going to fall off and be sequestered as carbon, as opposed to the amount that you want to use make into a valuable commodity?
Well, up to a quarter of the seaweed on a offshore seaweed mariculture will fall off the platform during growth. And we have some of the deepest platforms so far at 350 meters depth in the Pacific Ocean. And that we've already established the sink rates of these at over 1,000 meters per day. So that results in a matter of hours getting beyond 300 meters, and in less than a day getting beyond 1,000 meters, where it remains for centuries in most parts of the deeper ocean.
Mm-hmm. Well, thank you. Okay, let's go back to the main the first item on our agenda, that is the rock dust. And I wonder, David, would you have had experience as a farmer using rock dust? I remember coming across something that you wrote extolling the beauties of something called black shale or something black. As a matter of fact, that may be in the background of what Tom's photo shows.
I think you're correct about that rock behind Tom being the one that I trialed. It does have an amazing impact on the growth of a greenhouse crop. What I did is incorporate it at a relatively low percentage into the potting soil, and had quite a good response from it. It provides a lot of trace elements. I think that's the key to the how it works. Now that remember, those experiments weren't designed to trap carbon. They were looking at that rock for the quality it has for growth enhancement. But in fact, that rock does have carbon capture capabilities, quite significant actually, about at least a couple 100 pounds of CO2 per ton of the rock. And I think what Tom had said and Brian earlier, you do need a comprehensive approach to the problem of CO2 capture. It's not as simple as just saying, "Oh, grind up rock, throw it out there, and it'll do its thing." And my role in this whole thing has been to basically do a life cycle analysis of some of the rocks, and that is an eye opener because you've got to be honest with yourself and look at all the ancillary costs. And in terms of CO2 that generating that rock can cause. In other words, you got a mining, you got a crushing cost, you've got a drying cost, you've got a bagging cost, you've got a shipping cost, and all those things use energy generally in the form of a fuel, which gives up CO2 into the atmosphere. So what you started out with, you might have started out with 400 pounds per ton of carbon capture, but you may end up with 200 pounds per ton of carbon capture.
Yeah, I actually was watching a video a couple of days ago where there is a report on a study done in Brazil about the net effectiveness for CO2 sequestration. And they say that if you have to transport the rock more than 500 kilometers, it's not worth it.
Well, let me interrupt you on that one.
Yeah.
I actually saw that study, and there's a mathematical error in the study.
Oh,
Believe it or not. I don't know how he did it. It was a very good study. It's very accurate for the most part. I went through the whole thing, and I picked up a difference by a factor of 10 between his reported values that were in the study and then what he actually concluded at the end. And he got bogged down in somewhere in there, he made literally an error factor of 10.
was it to the good or to the bad? I mean, are we happy about his mistake, or should we?
Yes, we're happy. We're happy. He completely overestimated the cost, the CO2 cost of transport. And it's just a mathematical error, and he actually referenced it correctly later in the report. So it was just one of those things that got out there, and it became like gospel. And it's hard for me to believe that it actually happened.
Okay, so it is not true that if you
no, it's not
more than 500 kilometers, don't bother.
You can transport via ship 3,200 miles and still have 75% of the CO2 capture still available. Mm-hmm. So just to put that in perspective, yes, it does matter, and hauling it by truck matters a lot, because then you're talking 400 miles, 500 miles. You're going to chew up a good portion of the CO2, and also keep in mind that CO2 is not the only thing you're considering here. It's the cost to the farmer or the gain to the farmer. Just like Brian was saying, you can get 25% yield, but if you chew that up in shipping to get the rock to the farmer, well, you're not doing the guy any favors. Mm-hmm. So
Brian has his hand up. He's obviously keen to correct somebody. What's up, Brian?
Well, I think the life cycle cost is really important. I just wanted to add that we see approximately 20% life cycle costs in terms of the carbon cost for cultivating the seaweed, for bringing it in, converting it to a biostimulant, for example, and getting it to agricultural operations. Now, transporting a liter isn't very expensive, but I think David's right. You want to be shipping by sea, by ship, and then as necessary by rail, and minimize the amount of truck transport that's needed for these soil amendments.
Mm-hmm. Okay, that's good to know. Now, actually, I don't want to get into making a criticism of anybody's approach, but my original thought was, why don't we take the biochar? I mean, why don't we take the seaweed and make it into biochar, and use that form of biochar? But I believe that that there's a problem that the nitrogen gets excreted or burned off while you're pyrolizing the material.
Yeah,
And-
you're exactly right, Meadow. There's a double problem. You pyrolyze the nitrogen back out of the mix, and then you lose half your carbon to burning to pyrolyzing it.
Mhm.
So yeah, there's no point in taking something as high a quality as seaweed and then pyrolyzing it.
Mhm.
You
Okay.
just I'd rather get my seaweed from Brian,
Mhm.
direct. Yeah.
Okay,
Yes.
well, here's the alternative, and that is this thing called biostimulants, which Brian has already mentioned. Is that a more effective, more transportable form of application of the seaweed?
It's a great application for it. It's really an extract Brian's talking about. And when you make, and I've used the seaweed extracts. I know what they're like, and what they effectively do is they inhibit the inhibitory processes that happen in plants that are under stress, cut down the yield. And when you spray something like the seaweed extract on them, you provide the enzymes that kind of override the inhibitory signals to the plant. So the plant says, "Oh, it's a beautiful day. I'm going to grow more," as versus saying, well, "I'm hurting. I'm not going to grow as much." So that's really what the extract does. That in turn captures more CO2. Absolutely.
Mhm.
The seaweed itself does capture CO2. When you're growing it,
Yes.
Yeah, it certainly does.
However, I mean, originally my thought was, let's just make all this seaweed and use it, but then it goes, it goes back into the atmosphere very, very soon. So the only reason you would want to use it would be if it also does a lot of good for the soil and fertility
Right.
and the food production. But also if you combine it with something like biochar, which will keep it from going back into the atmosphere. That's my theory. That otherwise you're doing a short. I have the same concern about forestry, because yes, you can raise a lot of trees, but they're all going to fall over and die in short, few years. So you're not getting anywhere if that's all you're doing, unless you make it into something like biochar, which is permanent. So Brian or Tom, Tom, you're
I'd like to expand on some of the physical qualities of using seaweed. In other words, the raw seaweed, if you take the seaweed and apply it into a soil, and this has been done for many years. This isn't exactly a new thing, but you can improve the quality of the soil itself, and especially where you have a lot of environmental stresses, whether it's, for instance, as an example, where we have a lot of wildfires going on and steep slopes are denuded of vegetation. And then in a short period of time, this is followed by heavy rainfall, which causes landslides and things like this. The seaweed itself has a function that could actually stabilize soils, whether they're stream banks or ocean, eroding ocean lines or other types of soils, even broadacre farming where there's a lot of stress, environmental stress. So there's potential beyond biostimulants, beyond extracts, just the raw material. And again, it's going to come down to proximity of the material to the fields. In other words, what Brian was talking about for transport and logistics, or combining the material into formulated goods so that the farmers could use that, or the growers, or whoever it is that's involved in land management, so that they can put out materials together in one pass that would actually do more than 1 year's worth of work, which is one of the great benefits of all of these types of materials. Biochar, seaweed, rock dust have very long benefits over many years. there's been some studies to show that you get 20 years benefit for one application in forestry and other types of
20 years benefit in terms of the fertility of the soil, how productive it is, right?
right, you know, and the growth of trees or whatever it is you're trying to accomplish. And I think there's going to be more and more interest in more permaculture type management. In other words, converting some of the annual production into more permaculture or mixed permaculture. And so these sorts of techniques and with these materials where you establish a permaculture type environment, growing environment, whether you're planting trees or shrubs or combine perennials and annuals together, you want to maximize the benefit of every time that you go out to put any sort of input other than the plant itself in place. And so this sort of work that we're promoting, whether it's biochar, rock dust, seaweed, or combining with horticultural actual growing plants where the plants themselves are providing the energy through photosynthesis, etc. This is the sort of thing where you will really gain ground on addressing climate change in terms of the significant losses that the loss of temperate zones represent. In other words, we're sliding backwards at the same time that we need to actually be gaining ground. So these types of materials will do that as long as they're looked at in a whole system approach. And I think that's the discussion we're having today.
Well, we want at some point to have some numbers, and I don't dare try to calculate these myself, but one of the things people want to know is how much value we're going to get in terms of carbon sequestration per ton, let's say, of rock, under what circumstances and so on. How much of the world's excess CO2 can we remove from the atmosphere now? If everybody, or if a certain number of farmers, let's say in Canada, applied this. Now you say they only have to do it. Are you saying they only have to do it every 20 years?
I'm saying that in certain circumstances where a single application is all that you're going to get, they will get 20 years worth of benefit. Whereas if they're going out every year, or they can work these materials into crop rotations where they may be in a 2 or 3 year or even longer rotation, they can come around to that ground every 3 or 4 years or 5 years. In other words, they can work these materials into agronomic benefit based on their management strategy. That's the beauty of these materials. So you can put these materials into an economic framework, which is what David has done, doing the life cycle analysis and transport analysis and the horticultural and agronomic benefit analysis. We can actually show the farmer, if you do these things, these are your return on investment, including transport and logistics. So these are all measurable benefits, and it gives you permanence as well, which is one of the problems that we're seeing through some sorts of approaches where they're looking at just soil organic matter, looking at just the top few inches of soil for carbon sequestration. Those types of approaches can be reversed quite rapidly, especially if they're not accompanied by true regenerative management practices. In other words, if you just throw material out there and hope for the best, those benefits can be lost. So we're looking for permanence, and these materials can give you permanence.
And as I understand it, it really is economically worthwhile for the farmer. It's a good investment. They're going to get value from their investment, but and so you wouldn't really theoretically need to have subsidies from the government to get people to use it, because it's to their own advantage to use it. However, it might be that you'd need the government subsidies to get people to adopt it early. If they're cautious and they're scared to try something new, then the government might need to pay some people to take that initial risk so that they can show that it works. Is that a reasonable point of view or not?
Let me answer that if I can, Meta. When you do a life cycle analysis on this, I'm looking at the gain for the farmer, because if there's no gain, no one's going to do this. But the thing that you're talking about with the government subsidy, when you look at the end of it all, you might be looking at only $50 a ton benefit to the farmer. Okay, now that doesn't sound like a lot, except when you figure out that average farmer might make $100 an acre on his $1,000 an acre investment.
Mm-hmm.
So you add $50 an acre to that, and you've just given him a 50% increase in his earnings. Now that they're going to take notice of. Now, if you include the carbon credits, if the government were to step up and say, okay, we're gonna subsidize you getting this rock or this seaweed based on the carbon credit value of the capture, that might be $20 a ton in terms of what the carbon credits, but that $20 is 20% of the guy's income in the field. So it does make a big difference if the government does get involved and make it an incentive, and it doesn't have to be a large amount of money to make a big difference, as long as it shows up on the end in the guy putting the stuff on the field and getting the yield increase that he wants.
Mm-hmm.
So yes, very important that the government be involved, especially in the beginning.
Mm-hmm.
I think early adoption is where, if government has a role in this, it would be to put some of the largesse that they're already putting into other sort of crisis management and huge, annual outlays towards climate mitigation, not to continue to dole out subsidies, but to create the environment and the infrastructure, and including the distribution channels for early adoption. One of the problems that we're seeing right now, because the globe seems to be into a crisis, multi-year crisis environment, many of the supply chains and transport infrastructure, labor shortages, all of these things, fuel costs, these things are now compounding the problems of addressing probably the largest long-term crisis, which is the destabilization of the temperate zone, represented by climate catastrophe. So government does have a role, as long as they'll take an active view towards addressing an emergency by treating it as an emergency.
Mm-hmm.
Because if we just use the traditional trajectory of market development, generally to introduce anything new, you're talking decades. And to form a good, solid business around a new venture, that can be generational. That can be two generations, if not 3 generations. We just simply don't have that time.
That's
so,
right. Yeah, for sure.
yeah, there's a role. There's a role for organized investment, government or private investment, and it's a significant investment that's required. It's not a few $1 million to actually roll these things out. So yeah,
we'll have to do some real calculations. I know that Brian has been waiting patiently to say something. So let's hear what you have to say, Brian.
Yes. Well, Tom is right. There are tipping points that we need to address immediately. And they go from the fact that the Amazon, if you cut down another few percent of Amazon rainforest, the Amazon goes from a net carbon sink to a carbon source, which is terrible and nonlinear. Other problems include up in the Arctic, including Canada, as the sea ice disappears, you're now absorbing so much more sunlight during the summer that you'll melt the Greenland ice sheet, which is a tipping point resulting in 26 feet more sea level rise. Mm-hmm. So we're looking at tipping points in the soil, tipping points in the seas that need to be addressed immediately. And the best role for government is to provide this predictable and rising price on government to reward and incentivize the first 10% adoption of these integrative techniques for agricultural practices. Because quite frankly, we have to overcome agricultural sprawl. You've heard of suburban sprawl, but agricultural sprawl has an enormous effect on the wild forests of Canada and the wild forests around the world. And the reality is, with a revolution in food producing technology on land and in the sea, we'll be able to enable half of that cropland to be rewilded and to enable huge amounts of biodiversity to come back again. That's an enormous hopeful message for the future. In the meantime, we need to incentivize the first 10% of early adopters to enable these integrative soil regenerative properties. We have a better biological understanding of the soil today than we had just a few decades ago. So what was a chemical green revolution in the past millennium is now an opportunity to actually, through that improved biological understanding of the soil, rebuild healthy soil microbial communities, including inputs like rock dust and biochar and seaweed agricultural amendments, to build those healthy soil microbial communities that can tap into the mineral nutrients, actually fix recalcitrant carbon in the soil for decades, if not centuries, and ultimately improve the soil productivity at the same time. Now, there's something that you alluded to, and that is there is a short carbon cycle that involves seaweed being grown and rotting and going back into CO2, and a short carbon cycle on land, which includes crop residuals or residues that rot during the year and form carbon dioxide again. That's the short carbon cycle. But the long carbon cycle includes in the soils the recalcitrant carbon that's formed. In other words, there's a partnership between plants and healthy soil microbial communities. Those microbial communities unlock the mineral phosphate and the mineral nutrients, convey it to the plants, and the plants return and reward that with sugars and other carbohydrates that go back to the soil microbial communities, and those soil microbial communities produce recalcitrant carbon in the form of humus and other organics that can remain for decades, if not centuries. And that's where...
Tell me, you use this word recalcitrant carbon. You know, we got two different kinds of carbon, recalcitrant and ordinary, or what is recalcitrant carbon?
Yeah, that means longer chain molecules that can last for a long time. For example, we were invited to the Plant Carbon Drawdown conference at the Salk Institute and gave a keynote lecture on the marine plant carbon drawdown techniques. But the folks at the Salk Institute are actually researching varieties of plants that will produce, here's an example of recalcitrant carbon, they'll produce melanin in the roots of the plant. Now, you're familiar with melanin because it actually it gives a pigment to your skin and actually against ultraviolet. Well, it's also a longer chain molecule that lasts in soils much longer when you have soil microbial communities. The thing is, you have to keep those soils growing. In other words, you need a variety of plants and microbes in those soils to have healthy soil microbial communities remain and add more carbon and more carbon each year. And that's where the long carbon cycle comes in on land. In the sea, the long carbon cycle comes from seaweed that sinks to the abyssal seafloor, and literally it may be dissolved in that seawater. That seawater will take centuries to return to the surface where it actually is emitted again. So that's a long carbon cycle. And of course, the United Nations gives a carbon credit for any sequestration an average time scale of a century or longer becomes a certifiable carbon credit. So that's an essential part of what's going here. And our work with folks like Professor Johannes Lehmann from Cornell University have demonstrated that you can actually build soil carbon. And Professor Lehmann likes to call it carbon capital, soil carbon capital, because the biochar that you put in and the healthy soil microbial communities that you form in year one will pay dividends for decades after the intervention. And that's really key and magic, because you're making your land more valuable when you've got a more fertile land. And these integrative amendments are what will really enable those that land to become more fertile over time and overcome a lot of the losses of soil that we've had in previous decades.
I'll make an interesting observation in that the rock that's my backdrop for this conversation is a black rock, and the color of it is actually derived from carbon, which was deposited in very, very deep ocean sediments. And so the actual foundation of this somewhat miraculous rock, when you spread it on land, is the result of extremely deep sediments, carbon-rich sediments, because the carbon wasn't oxidizing and returning to the atmosphere. So here's a proof behind us that this actually can work, and not only in the maritime environments, but also on land. So I think these are real foundational principles that should be easy to describe to the Pugwashites or any of the other people that have a stake in shaping the future. The problem that I see right now is a lack of understanding of the long carbon cycle. In other words, how this is a geotectonic period that we're in. That's of extreme variability in terms of how it presents itself on the planet right now, but also requires an extremely concerted effort to mitigate the worst effects. And this is not something that is going to be over in a day. It's going to take 50 years, even 100 years of dedicated effort. That's a tough thing to sell to people that are used to their attention spans might be in milliseconds. So,
well, I agree, but my notion here is with these particular four interventions that I'm choosing, I'm picking them because I think they're things that Canada could do without having to organize the whole rest of the world, and could do something within 5 years.
Mhm.
So my sense is that, you've got rock dust. It wouldn't take very much effort for people to pick it up and, mix it in and spread it around. So we know that something could be done within 5 years.
well, we have pilot projects right now. There's in Saskatchewan, there's a mountain of material of a very high quality rock dust that even the enhanced rock weathering academics have been studying for several years. Stockpiled in Saskatchewan, right in the middle of broad acreage farming with regenerative growers all around. So
But I've heard also that mine tailings can be used. And I tried to find where are all the mine tailings in Canada. There's no map that I can find. So if anybody can tell me where they're keeping their mine tailings.
Well, the tailings aren't something that you can just look at the yellow pages and find. And the rock dust that's actually that was transported up to Canada for this project is a form of tailing. It's an undersized material. It's a byproduct from commodity aggregate production. So there are a number of resources that are available in the hundreds of millions of tons if you know where to look for it. But that's just the beginning of the project. That's not the end of the project. So each one of those tailings has to be characterized for mineralogy, carbon capture potential, transport, logistics, and all the rest of these things. So there's a lot that can be done and should be done, but we don't have to wait. I mean, these projects are looking for sponsors. They're looking for benefit as far as demonstrating these things at scale. And as I said, you actually had Ryan Brophy out there in one of our previous interviews, and he's a trained agronomic specialist and touches hundreds of thousands of acres a year of farmland in Canada, and understands all of these materials, including the black rock and the basalt, in agronomic settings. So I don't think that this is theoretical anymore. It's really needs the support now rather than 2 years from now.
I agree. Okay. In fact, we also have people at the University of Toronto who are willing to do support work for us. I've been talking to 2 professors there in the last couple of days, and one specializes in life cycle analysis, and even says there's going to be a course offered in it, so they might take us on as a class project or something if we asked.
I think one of the points that Tom brought up earlier about the benefits of seaweed supplements, including seaweed foliar biostimulants, is stress resilience. And I think that's really worth touching on, because in this day and age of climate disruption, we've got a number of enormous stressors to deal with. Not only the normal stressors you'd have from monocropping in an agricultural context, but beyond that, you've got drought and you've got heat that you're dealing with on an increasing basis, as we've seen off in British Columbia just in the last summer. And being able to manage the drought and heat resilience is absolutely essential. And we've seen enormous improvements in agricultural yields during high stress conditions. And we've, especially with drought and heat, we've seen it with rice fields in Southeast Asia. We've also seen it with row crops, even in Canada, for example. I think that can have a transformative effect as we are faced with increasing stressors from climate disruption. There's a great opportunity to effectively build more resilience into our agriculture.
Tell me what that resilience would look like. Are you talking about like, can they tolerate more salt? Can they tolerate more heat? Is that the kind of thing that you would measure, trying to ascertain the resilience of a piece of soil?
Yes, drought stress and heat stress are well documented in plants, and you can measure those quantitatively. And they effectively, when you do trials under stressful conditions, that's where you see the biggest differentials between baseline production, even with replete NPK fertilizer, and these plant growth regulators that are present in the organic seaweed foliar biostimulant products. You can see 15 to 30% higher yields in a high stress context over replete NPK application.
Mhm.
That will also benefit the consumers. In other words, if you translate stress resistance, drought resistance, freeze-thaw cycle resistance in growing plants, which you can with the seaweed, you can do the same thing with a micronutrient boost and mineral through green mineralization. That will translate also into resiliency of whoever is going to be consuming the crop, whether it's forage for livestock or whether it's human beings, where they're getting the secondary and higher plant metabolites that these plants are actually producing that they may not otherwise be producing in the absence of these micronutrients and biostimulants. Now you're starting to talk about the benefits to society, whether it's health, the health effects of the individuals in their own lives, or the health effects in raising livestock of any sort, whether it's poultry or beef or any sort of meat product. These sorts of things can be quantifiable, and the benefit is there in the form of returns on investment, whether it's human populations or livestock. So these things will continue to be necessary reactions, because the pharmaceutical approach to health is proven to be a failure over time. We see it right now through the increased morbidity in Western populations. So these sorts of things, the health will start in the soil and in the ocean. And I think that it's not science that needs to be proven. It's science that has been proven. It needs to be demonstrated at scale.
Mhm.
So that's where we are with these things here.
Okay, now here we have in the chat, I think Adela has problems with her microphone or something, so I'm going to read her question, unless she can come in and do it herself now. She says, how would this technique translate to the third world? Issues of transportation, source of rock dust. Seaweed is presumably available in every ocean coast area. Anybody want to answer that, how it applies to the
Sure.
third world?
We're working in the Philippines right now, and yes, seaweed's enormously valuable. Having those micronutrients, whether they're coming from the sea or coming from existing mining operations, are helpful as well. And it's a whole approach that includes those soil microbial communities. That's enormously important, and I think that it does translate very well. In fact, we're able to, because seaweed can be labor intensive, we're developing the seaweed foliar biostimulants in the developing world first. And it's something that we could initially import into Canada because it is very catalytic and effective at small quantities. And then furthermore, that can ultimately turn into local production of seaweed as well, where ultimately there become domestic industries for the biostimulants that go directly into the agricultural amendments. I do want to touch on something that Tom mentioned, and that is the effect of these integrative approaches on livestock. And I've seen studies in Canada, for example, that show that if you get rid of the antibiotics that they feed chickens now and instead use seaweed as a feed supplement, it actually improves the immune system of the chickens so much that their survival rate is higher on the seaweed supplemented feed than it is on the feed that has antibiotics in it. So instead of producing antibiotic resistance, and MRSA and all those other problems, we're actually building healthier chickens that have a higher survival rate than if you use antibiotics. So that's what we have to get off of, is better life through chemistry only, better life.
Right, but that's not just chickens. I mean, the thing that I've read is that certain kinds of seaweed, if you feed it to cows, it stops their belching and reduces the amount of methane that they're producing, which is a very important. I think cattle are really a very significant source of methane. So yes. I didn't even mention that, but I think you ought to talk about that a little bit, Brian.
Some 40% of all agricultural methane emissions come from the rumen of ruminant livestock, and those enteric methane emissions of ruminant livestock represent a huge emission. Did you know that 11% of the feed energy for these livestock actually goes up in smoke as methane? That's how much energy it takes to produce methane. So if we put a cork in it, and that is by adding a 1 to 10% feed supplement to ruminant livestock, including dairy, including cattle, including goats and sheep, you can actually eliminate most of the enteric methane emissions of ruminant livestock, and at the same time have several percent more feed energy available for the animal. And that means your feed conversion ratio can improve. And when the feed conversion ratio improves, that's dollars in the bank, because even a 1% feed conversion ratio improvement can double the profitability, as David had mentioned, double the profitability to the farmer. And so ultimately, these regenerative techniques have an enormous positive net present value economically, as well as improving our ecological outcomes and our greenhouse gas reduction.
Thank you. And I had one other brainstorm that I tried out on you by email, because I didn't want to bring it up on the talk show until I ascertained that it wasn't totally crazy. And you say it's not totally crazy anyway. And that is that apparently, for some reason, Hudson Bay is just overflowing with seaweed now. And, the problem is the indigenous people living on the shores are having a hell of a time because their livelihood has been destroyed by the lack of ice. They have trouble there. And we're going to, in another one of these projects, we hope to be able to restore some of the ice to Hudson Bay within 5 years, and by spraying seawater over it. But that's not going to do the whole of Hudson Bay, which is a huge body of water. And those people still need some way of making a living. So one of the thoughts I had was they could harvest a lot of that seaweed that's almost in excess growing there now. And I believe there's a train, a freight train that goes from Churchill, Manitoba to Thompson, Manitoba. And they could, but what I was suggesting was maybe you could set them up with some sort of little factory where they could make this biostimulant out of the seaweed. So we could have these people make a living by harvesting some of the surplus seaweed from Hudson Bay, making it into extract, and sending it to David to put on his garden.
Well, that's a great point, Meta. And I think there's two reasons for it. One is there's far less ice in Hudson Bay, and that means a much longer growing season. And there could be runoff into Hudson Bay that would increase that nutrient level. And the seaweed does a fine job of trying to absorb those nutrients and turn it into useful carbohydrates. And I think you're correct that you could take the raw seaweed from Hudson Bay, and we've developed a transportable containerized biorefinery that will produce multiple food products, feed products, and fertilizer products, including biostimulants, from the raw seaweed. And then you can ship container loads of each one of those across Canada by train and enable those agricultural amendments to have transformative results. It turns out seaweed's pretty good for people too. I eat a few grams every day, and look what happened to me. So
Okay.
I think as a nutritional supplement, it is highly recommended. I'm amazed at how it improves the digestive system, and the knock-on effects of improved immune system don't apply just to chickens. But not all of us are not spring chickens, but we can get the improved immune response that we get from eating a bit of seaweed every day.
I started eating it myself, little snacks,
Wanna-
Anyway, this has been
I want
fun.
to go. I'd like to go back to the second part of Adele's question about the rock dust and transport. In other words, how does this work for third worlds? Now, my company, Rock Dust Local, developed a regional sourcing model for taking rock dust where it is and delivering it into the nearest locations. And we also developed long, transport models. And the benefit of these types of rock dust is they actually occur globally. So they're not concentrates that only occur in one place and need to be transported all around the world. Many of the best of these broad spectrum rock dusts occur in many, many places,
Mhm.
and on all the continents, and also on some of the island environments that are volcanic in origin. So there's a very, very good potential to use the same local model to reduce transport and logistics. And also, once you get the material onto ship, you can go great distances and still maintain a good amount of the CO2 benefit once it's landed. So there could even be a transition period where you're starting to ship initially long distance, and as you develop these technologies and manufacturing capacities overseas, you start reducing dependence on importation. So these things are very doable.
Mhm.
Transport modeling's been also done, and the metrics work. The metrics do work at scale.
Well, we're on to something, I think, and I'm gonna pursue it further. I think Pugwash will probably get back to each of you and say, tell me more. So we'll have other meetings and other opportunities to bring in other people who might have criticisms or alternative points of view. We want to listen to all issues that arise in this connection so that we know what we're talking about when we finally maybe go to the Canadian government and say, here's a plan. Okay, thank you all. It's been fun and really valuable. I really appreciate it. So carry on. Bye.
Thank you.
Thanks, man.
Thank you.
Okay.
Yeah.